So overview of today's talk. So the hybrid search, I'm going to focus on that one. Hybrid search limitations with that version, and then as well workarounds. For the workaround is a pagination and reciprocal rank fusion needed for hybrid search. And then also talk about the native support that is introduced later, specifically in version 2.19 and later. And also talk about semantic highlighting workaround, and then the feature that is introduced recently in v3.0, and then the high level architecture, how it works behind the scene. Then the last one is just the findings about the domain suggester or phrase suggester that we found during our implementation. So first of all, let me start with hybrid search. Basically, what is hybrid search and why we need hybrid search at all? So hybrid search is, just put it in simple words, is taking the traditional keyword, exact matches, BM215, for example, and then combining with semantic search or vector search. And then once you take both results and combine together, and then you have the single result sets. So why we need hybrid search at all? But so this is because we want to have more relevant results. So whenever you search, so you have more relevant to your search query. That's the behind the scene, that's the. And so that's the more relevant data set, keyword search and semantics combining that one. And with the v2.17 version of OpenSearch, there is a hybrid query. You can do hybrid search, but there are two main basic limitations. One is the pagination, because with that version, pagination is not supported, because whenever you do hybrid query search, it just returns all results at once. So you have to do all the pagination on your own. And then another one is about the merging one. So behind the scene, OpenSearch just only supports the min-max normalization score-based technique for the combination. So because you have another technique which is called the rank-based one. So based on the algorithm reciprocal rank fusion. So it wasn't supported with that version. So based on these considerations, we decided to implement on our own hybrid search. So because of these limitations. And so yeah. So for that one, so how we implemented that hybrid search. So we took a very simple approach. So what we do is we run lexical search, multi-match with the OpenSearch 5. And then another one is vector search, that's canon search we run. And then once we run the two searches and we have the result sets, then we merge together using our custom reciprocal rank fusion service. And then we get the results and we run that one. Let's before diving into that one, showing the code snippets, just let me a little bit about the background of the reciprocal rank fusion. What is that one? I know many of you know that one. And the reciprocal rank is basically, in simple words, is an algorithm. So based on the position of the documents. So if, let's say you have the set of documents, and the documents are in the beginning, let's say, of the document, they have the higher rankings or higher importance, and so ranked higher. And then in this context, so rank is basically the position of the document in the result set. And the reciprocal rank is basically the inverse of that rank. And based on this formula, 1 over rank plus k, we calculate the reciprocal rank score of each document before merging it. And then once we merge it, then we basically, based on that one, we basically sort it and descending order, then we return it. But there is a one, so let's say we have two result sets, a lexical search result set that's ranked separately, and we have the vector search results ranked separately. And we want to combine together using the RRF, using that formula. So we first initially calculate the reciprocal rank score for each document in the lexical search, and then also calculate for that semantic search as well. Then sometimes we might get, sometimes, but often we get a similar same documents in the same lexical search as well as vector. So we just add up the scores, reciprocal rank scores. So that means that if if the document appears in a lexical search and as well as semantic search, and then it has higher ranking in our end results. So so once we combine together, then we just sort based on this reciprocal rank score, and then just return the result. So let me just so next one is gonna be this one. So this is basically the very high level snippet. So how to do that search. So we have the search query and then page number, page size, the other attributes. So then what we do is, because here we need the page number and page size, because the pagination also does not work. So we have to handle the pagination part as well. So in that case, we just multiply page number and page size in order to get the total number of search results. And then for the lexical search, this is the lexical search call we do. So to get the lexical search results, it's behind the scenes is just a multi-match with some boostings, all the other parameters. So we get the result set size variable, the number of results. And the vector search, similarly, we do that one. We call the vector search. Behind the scene is the canon, top canon. And then once we merge it, so we do have our custom RF service to basically merge the results by taking those two lists. And so going to that RF service, so what we do here is basically in that formula, if you recall it, a K is a constant. So by default, it is 60. So a little bit I'll explore why it is 60, and then there are a lot of research papers. So if the constants are like K is small, so basically it gives better results. So we have to keep the K as small as possible. And so in our case, it's 60. So just by default is 60. And then so we take basically the lexical results list and the vector results list. And then what we do is we walk through the lexical result sets, and then we calculate the reciprocal rank score. And then similarly, we do that for the vector results list as well. Whenever we have the same document ID, and then we just sum up the reciprocal rank score here. And then we just revert it, and we just return the results by this service. And then in the here is the for the pagination part, we just did the trick about how to handle the pagination part. So we use here Java's APIs, showing ones. So what we do is we use just a skip and the limit one, because we want to handle the where you are right now, pagination of page number, and you have to. So here in the skip, we skip all the documents up to page number -1, and then page size, and then we can return only the limit here, the page size, because we want to show only the page size document. Let's say page size is 10, then we will just keep here just only the 10 documents to show. And so this is how we did with the pagination one. However, so once we've done this part, and then OpenSearch introduced in their V2.19 improvements, huge improvements for their pagination, and then as well as the reciprocal rank fusion. So they introduced this both. For the reciprocal rank fusion, for the normalization, they introduced that one. It's in the PR, but I'm not going to go into that one. So it's just like it exists, so it supports now. And then also pagination as well. Pagination basically is controlled by the pagination depth new parameter in the hybrid search query, and there's also from size parameters. So this is basically how to create. So you have this hybrid search query, and we wanted to use this reciprocal rank fusion algorithm in our hybrid search query. So in order to use that one, first we have to create a pipeline, and then use that pipeline in our hybrid search query. So to create that pipeline, so we have to specify these two things here. For the combination, so we have the RF here, RF technique, and then provide a rank constant, that's K. So if we just skip this constant, it's going to be 60. So this is optional, but the first one is the RF is mandatory. So we have to provide RF and then K as well. So once we create the pipeline, then we can do the hybrid search query. Here is the hybrid query, what we do. So here with the search pipeline, we provide here the RF pipeline. That is the reciprocal rank fusion pipeline that we want to use to combine results. And in the hybrid, what we do is we have the queries. This queries basically takes multi subqueries. In our case, we are using only the two ones. One is for the lexical one. The other one is for the semantic or the vector search ones. But we can have multiple subqueries in the hybrid one. So then, for the lexical part, lexical search. So we have the query. Let's say we provide the query, and then for the fields that from what we want to search, okay, just title, description, whatever the fields are, and then type is the best fields here. That we are saying that, hey, any of these fields match the query, just return that one. So that's why we are using the best fields here. By default, actually, this is the best fields anyways. And then for the vector search part, so we are using here nested fields, because in our index, we have long paragraphs. And then we basically first we use the chunking stuff. So when you have the long paragraphs, first we split into multiple chunks, and then that's why it is nested. And for the KN part, so we are just focusing on only the chunks one. So chunks is basically nested, and inside the chunks one, we are focusing the embedding subfields. That's basically vector generated by LLM. So it's in advance generated and the index in OpenSearch. So we assume we do have that part. We handled one, and then so once we generate, we pass that one here and as a vector, and then K in our case is 100. So we want to return top K search results. So yeah, from this one, so the hybrid query, this is how it works. And for the pagination part, so as I mentioned before, pagination is controlled by this pagination depth parameter. So basically, what it does, pagination depth is the maximum number of results to retrieve from each chart for every subquery. Let's say we have in the queries part we have two subqueries, then we have to return times 2 basically, because for each subquery we have to return, and for each chart, if you have multiple charts, then you have to return for each chart in each data node as well. And this happens before merge. Then first you get the results from each chart for each subquery. Then once you have the results, then you do the from and size is basically a sliding window. So how many data you want to return to the user, and so it's just like a slice between the sliding, just moving that one. So how many data sets we have to return to the user. So here is the diagram, the high level architecture of the pagination, how it works. Here, let's assume we have 3 data nodes. And then each one contains just only one chart for simplicity. And we have a coordinator node or master node. And so what we do is here that we provide the pagination depth of 20. So it means for each subquery, here we have the match query and the canon query. And for each subquery and for each chart, we return this amount of search results. So for match query, we return 20 results, 20 documents worth. For the canon query, 20 as well. And we do this the same for all data nodes. And then this is the data nodes, but they're all is handled by the coordinator nodes. So calculation, combination, all got handled by the coordinator nodes. And the normalization processor basically takes the match query. So in our case, it's 60 because each one returns 2020. And then the Canyon query is similar, is 60. So we have 120 results now. So, but this result is not yet merged. So once the normalization process merges, we might have some duplication as well. Duplicates occurs in the lexical storage as well as semantic. So it's basically reduced, the number of results reduced. So let's say we have 100 results now. After merging it, let's say duplication, all kind of stuff. And let's say we have 100 results. And then the from and the size controls that 100 results. So it says, say, hey, from the 5 one, and then just get only the 10 results. And then you just slide that one up to you reach the 100th one. But once you reach the 100th one, let's say, then there's a huge limitation because that one, the pagination one, is the fixed one. So you cannot dynamically update that part. Because if you update that part, so you might get inconsistent results. So we have to be very careful what kind of number we choose, depending on the data nodes, how many data nodes we have, how many shards we do have, and all kind of stuff. So here is how we use it in practice. Pagination depth. Basically, under the hybrid query, you just provide the here the value and the variable here, and then it works. That's in the query system or that part. And so yeah, pagination, limitation is the one because of the fixed number. So if we reach the last available page and then we get this error, basically we reach the last page, we have to increase the pagination variable. And so so from this one, the OpenSearch documentation based on that one. So it's better before using that one, it's better to use first benchmarking, do the benchmarking in order to decide what kind of number we want for the pagination depth variable. And then we can do some iterations later on. Because it impacts on the CPU as well, because whenever you have a lot of shards and a lot of queries, subqueries, then it increases the number of results to return, because it does for each subquery and for each shard. So yeah. So that's about the hybrid search limitations and then native support as well. And then next, focusing to semantic highlighting, because this is another crucial feature we have, because we have to implement on our own before the native support in OpenSearch. It's just a basic background what is semantic highlighting. Let's say we search for health problems, and then you got into that one, type 2 diabetes. So basically, you are not, even though you didn't search for diabetes, but it's still like a highlight that one. So it basically knows that semantically it's the same, like, oh, it's similar. You know, the context is similar. So that's how semantic highlighting works. So here I wanted to differentiate it as two things in semantic highlighting. The type of the one is semantic keyword highlighting and versus the semantic sentence highlighting, because it's for the keyword part, we just highlight the keyword here. Let's say if we search for health issues, then headache, diabetes are highlighted. So that's the keyword highlighting, semantic keyword highlighting. Whereas in the semantic sentence highlighting, we basically highlight the entire sentence if it is semantically similar to the search query. That's the one. So here in our case, health issues, basically both sentences contain health issues related to health problem related, so we have to highlight the whole sentence. And so, and in our like a workaround, custom workaround, we went with the semantic sentence highlighting, so highlight the entire sentence. So what we did was basically what we did is taking the top K first lexical search, we run it, and then let's say you have 10 pages or 20 pages on your first, so we run that one, And then simultaneously, we run can search for each document ID. So, or we could do for all the 10 documents, we run the can search at the chunk level here, and to basically return the best relevant snippet or chunk one. This is the way. So first we have the K lexical search we run, and then for each document ID, we filter that document ID so that, you know, for example, because we may have long paragraphs and then it has multiple chunks. And so even though we filter it by document ID, so this document ID might have multiple chunks. And then we want to take basically best chunk here, which one is the relevant one. That's the idea. And so, and then for that text chunks, we run the can search for document. And then for the chunks, of course, we do have embeddings already in our index for each chunk. And that's done by the search for the text embedding model. And then for the query as well, we have the embeddings. And so we do the can search here. It is a cosine similarity or dot product. We do that one. And then out of that one, so we return the best relevant chunks, semantic limiting. And so we return a pair, document ID, and then chunk. And then to the user, it just, you have the basic lexical search result. And then under that one, so you have the chunk that's relevant and highlighted. That's what we did. So this is basically the two calls that's done on the UI side. The front end basically calls these two calls, lexical search one, and then for each ID, it calls the can search. That is the one. So, and however, so in our in v3.0 OpenSearch, so OpenSearch released this semantic sentence highlighting in end of April or beginning of May. So they released this semantic sentence highlighting, basically using using a question answering model to highlight the entire sentence. So let's say this is basically a high level architecture of semantic sentence highlighting, how it works in OpenSearch, how they implemented it. This basically originates from the RFC. You can have a look in RFC and then all the discussions and all kind of detailed stuff. I'm going through a code by line, all kind of classes. And here is this is a high level. And then let's say we have the search request with semantic highlight. So we have to highlight this sentence. And then we have these two modules. One is the neural search. That's the hybrid search one. The module that handles all the hybrid search stuff. The other one is the ML Commons plugin. That module basically handles all the model inferences and talking to the model directly. So the hybrid search, in the hybrid search one, so the semantic highlighter is introduced. That's an extension of the generic highlighter. And then that one first validates the given query. If it's valid, like a query, as well as model ID, because we need the model ID for the semantic highlighting, because under the hood, we are using the QA model, question answering model. So, and then once configuration is validated, so we pass to the semantic highlighter engine that prepares the text. Basically, the query, and then you have the paragraph. And so basically, it extracts this query from the query type and then prepares for the inference, model inference. And then pass to ML Common Successor. That's a new class. It basically acts like a bridge between the hybrid query module and the ML Commons module. And so it prepares the inference request. Basically, inference request has only two parameters, search query and then paragraph. Is a full of text, basically. Here to note that one, this segmentation, basically the processing text segmentation happens in the ML Commons module. So once the ML Commons Successor passes these two parameters, basically, and then to highlight query translator, and then that translated basically passed to the text segmenter to segment that paragraph, because you have the full paragraph, and then basically it divides into sentence, so an array of sentence. So, and then also it has to check, so when to divide it. Actually, this is a custom code, so they basically tries to divide by the, let's say, dot, like if it's a full sentence or if it's not full sentence, exclamation mark sentence, like all cases, try to check all the cases. Then it segments into sentence. So now from that one text segmenter returns the text, and then you have the array of sentence, basically, the paragraph is split into that sentence. And once we have that one, and then for each sentence and then text query, it calls the QA model, the question answering model, and then gets the response. And here the QA model, what is that? QA model is a question answering, basically the text query, search query, and then the sentence. And then it just checks, hey, is it relevant or not? If it is relevant, it returns 1. If it's not relevant, it returns 0. That's what it does. It just returns 1 or 0. And then this QA model is basically trained on AWS datasets, and it is available on Hugging Face. So with the version v1. So we can use that model. It's based on BERT architecture. And also it claims that we can use any other like a model based on the BERT architecture. If we find one which has the same input and output structure, so we can use that any other model as well. So that's the one. So it returns 1 or 0, and then QA translated basically translates that one. So if it is 1, and then it says, okay, it's relevant, and then it takes the position of the sentence, where it starts, where it ends in the paragraph, and the offsets and the story and index, and then also positions in the paragraph as well, because we already split into array of sentence, so you have to know this sentence position in the paragraph as well. It adds that one because it's important that we in the end, we return basically a paragraph and then with the highlighted or sentence. And that's why we have to construct that variant in the translator. So once we pass that one, position and stored and end index of the highlighted sentence, we just return to the semantic highlighter engine to format the response, because we want to highlight that one. Maybe it is bold text or italic text. So it's just a formatting happens at the semantic highlighter engines. So once it's highlighted, then we just return the final result to the user. So let's say it's just a sample how it works to show that one. Let's say we have just only 4 data sets. The field text, it's called the text, and some paragraph. So we index into that neural search index. So 4 of them. It's just ChatGPT generated text, and it's about some health issues or the health problems of the users, etc. And so then we want to perform the semantic sentence highlighting here. Here's a notice we have two. The first thing is the neural part. So we use the neural query type of neural because if you use the neural one instead of the vector one or semantic one, basically it handles the embedding as well. On the fly, it generates the embedding side. So on that one, so that's why we use the neural one, but we would have used the semantic one as well, but we have to provide the embedding here. So here we have to provide the model ID for the text embedding. So how to generate the embedding basically. So in this case, we're using the sentence transformers or mini-LM, L6 version. And this model ID basically how it is generated. So OpenSearch offers Task API. Through Task API, first you deploy your model, and then once it is deployed and created and ready, then it returns the model ID. So we have to use that model ID here. And for simplicity, the K is the 2, so we want to return just 2 best relevant results, the semantically highlighted. And then for the query text here, I'm using use health problems. And then the next part is the highlight part. So this is another model, just only for text meta model. And then this is for the highlighting part. So we have to provide here the type of the semantic one. So that is semantic highlighting. If we skip this part, it will just use the keyword highlighting. It's like exact matching. Then another options one, mandatory one, model ID we have to pass here for the model for the semantic one. So in our case, we're using the sentence highlighting model. So it's available on Hugging Face, so it's called the OpenSearch Semantic Highlighted V1. So within that model, so once we do that one, we get some results here, 2 results, as K was just only 2. The first one is the first sentence is highlighted. So use today face more health issues. So we search for the health problems here. So it should be similar to that one. And then here the EM tag by default is EM. So also it supports the other tags as well, strong and bold and all kind of stuff. And the another text is like highlighting double 2 sentence here. Yeah. So this is the semantic sentence. So let's go. So yeah, the last part. This is the last part. Did you mean suggested? This is actually not a limitation. Okay, so before diving into that one, did you mean? What is the do you mean? Just to recall, so if you search for something and then you have some typos, and then in the search result, it just like offers you, okay, did you mean this London weather or something like that? So this is the did you mean? In order to implement that one, did you mean? We basically took an approach of using phrase suggester, basically for the phrases we want. And based on the OpenSearch documentation, it says, this is just our findings. It says like it uses this phrase suggester uses n-grams chain to suggest phrases on the corrections. But without n-gram, it turns out that without n-grams, still works, phrase suggest works. So we have just plain chain, like it spells for the spell checker, like standard tokenizer and analyzers without n-grams. So it worked fine. And so then documentation, I think so that the correction is fit it doesn't necessarily use n-grams, so it's optional. So because behind the scene it used the model so to offer you the corrections, but it's not mandatory to use n-grams. And yeah, and that is it. So